Hi everyone, this is the Engineering Chicks. I'm Ashley and I'm here with Emily, and today we're going to talk about different kinds of simulations. So the three we're going to talk about are discrete, continuous, and Monte Carlo. So first, discrete event simulations model the operation of a system that has events that occur at a particular instant in time and then marks a change of state in the system. For continuous, it's a model or system that continuously tracks system responses. And then for Monte Carlo simulation, it uses repeated sampling in order to determine the probabilities of different outcomes in a process.
So going into a description of the three types of simulations that Ashley just defined for you, we have the discrete event simulation, and this is an event-based simulation. The simulation is able to keep track of the system statistics, and then it's used a lot of times for modeling queues, and that's because discrete event simulations, they simulate things that are countable, and queues have countable data such as wait time and number of people in the queues, and data that's countable. Then we found this refined method for discrete event simulation, which is a three-phased approach. This is a new method that's being used. And so the first phase is jumping to the next chronological event. And the second phase is kind of executing all events that are unconditionally occurring at that specific time. And the third phase is executing all events that conditionally occur at that specific time. So just kind of a different approach to the basic, just event-based simulation.
And next we have continuous event simulation. It's a computer model that continuously tracks a system's outputs, and then it uses formulas that are normally differential equations. So they model complex, continuously changing systems where a change in one equation changes the entire system. So it's generally a more complex system than you would use in discrete modeling. So it involves fitting a curve to a set of points, and if it's applied to a discrete system, it will most likely produce an error. So if you're modeling number of people in line, it could produce an answer of 1/3 of a person, which obviously doesn't make any sense. And it's used to predict rocket trajectories, used in flight simulators and jet autopilot systems, and used to monitor flight dynamics.
So the next simulation we're going to talk about is the Monte Carlo simulation. And Monte Carlo can be used in a plethora of different careers and fields, and like finance, engineering, supply chain, science. It's used to understand the impact of risk and uncertainty when you're predicting models, such as forecasting is a great example of this. And then it uses randomness to solve complex problems. And many problems can be solved this way, and it solves problems that have associated probabilities. And then the results of Monte Carlo simulations are based on repeated random sampling and statistics, and they're generally used when there are a large number of unknown parameters. So now we'll talk about the examples. Our example for the discrete event simulation is a queuing system. Earlier I said that the queuing problems are a common problem that discrete event simulations are used to solve. So our example is people arriving at a DMV to be serviced by the teller. And so in this example, there are two system entities, which is the customer queue and the tellers. And so with that, there are also two system events. So these events are when customers arrive and then the customer departure. And then there are also two system states that are changed by the system event. So those are the number of customers in line, which is the queuing area, and then the teller status. And the teller status can either be busy or idle. So they're either with or without a customer. And then there are two random variables that will be used to model the system, which will be the customer arrival time and then the teller service time. And you can use discrete event simulation to simulate this DMV experience, and you can get a lot of really useful statistics out of it, such as your average wait time, and a big thing would be finding out if your tellers are being idle or not, so you can find the optimal number of tellers for a certain time of day. So if it's busier, you're going to need more tellers, and if it's less busy, if it's not busy at all, you don't need as many. So this discrete event simulation can be used to analyze and simulate this type of a problem.
So an example that we found for the continuous simulation is called the predator-prey model. So this type of simulation is used a lot in modeling populations because they're complex and the factors feed off of each other. So with the predator and prey, if the prey population is rising, so is the predator population, just because they have more food to eat. But eventually, the predator population grows too large, and they end up eating too much of the prey, so there's not enough. Then the prey population shrinks, and as a result, so does the predator population. So the change in each population has an effect on the other, and it's continuously changing. And at first I was a little confused because I didn't understand why this was different from discrete, but it does count the number of predators and prey like a discrete model, but at the end it creates a smooth continuous function that's simple and useful for forecasting the populations.
So our final example is our example of the Monte Carlo simulation, and we found the traveling salesman problem to be our example. So in our classes we've learned about this problem, but Monte Carlo has its own unique way that can be applied to solving this problem. So using Monte Carlo, we can minimize the total time needed to reach each destination. And we all know that travel time is uncertain due to things such as traffic jams, the time of the day, if it's like 5 o'clock traffic, road work, or like special events like a concert or a basketball game is being held in the area, things such of that nature that are really uncertain. So you would use simulation to determine the time of the possible paths based off of a probability distribution function that would represent the range of potential times that it would take to get from each of the destinations. And then using that data in the simulations that you've done, then you can optimize the travel decision to find your optimal path. So this method for the traveling salesman problem really lets you take into the realistic uncertainty of the actual time it'll take you to get from one location to another. So you're able to take the uncertainty and based off of probabilities be able to come up with a optimal travel time for the traveling salesman problem. So we'll just talk about the history briefly of Monte Carlo. A guy named Stanislaw Ulam developed the Monte Carlo method, and he did this initially when he was sick. He was playing solitaire, and he wanted to calculate his odds of winning, and he tried to do this purely through calculations, and he saw that it was really hard. So he pondered and was like, I wonder if there's a better, more practical way to come up with the answer to my probability of winning. And so that's kind of when the Monte Carlo idea was originated. And so his initial thought was put into action when he started working on nuclear weapons. And when he was working on nuclear weapons, his colleague John von Neumann, he was able to actually program a computer to do Monte Carlo calculations. And this guy, another one of their colleagues, Nicholas Metropolis, was actually the person who suggested to them to call it the Monte Carlo approach or Monte Carlo method. And the reason being is that Ulam's uncle gambled at the Monte Carlo casinos in Monaco. So that's kind of like a brief history of how the name came about. And then Monte Carlo quickly took off, and lots of people started using it and adapting it to their specific fields of study. And so you've got genetic type Monte Carlo, quantum Monte Carlo, and sequential Monte Carlo, just to name a few of them. And as we know, there are a lot of ways that Monte Carlo is applied to fields today.
So real quick, we're just going to talk about some of the differences between these simulations. So for discrete simulation, it relies on countable data and requires an event to change the system and has to have like a whole number response. Where continuous doesn't have to have an event that causes any kind of change because the system is just naturally constantly changing and being monitored by the model. And it can result in any kind of response, including decimal places. And it can use countable data, but in the end it creates a smooth curve that's easy for forecasting and predicting. And for Monte Carlo simulation, it uses random sampling to predict estimated outcomes and probabilities, and that's the main difference there is using the randomness aspect. So that's all we have for today, and thanks for watching.